Yeah, so it's a sliding window problem. It's just wanted you to find the maximum number within this sliding window, and the window will slide one by one to the right, from the left of the vector to the end of the vector. Yeah.
Yeah, but it's weird, like we are speaking English, but the description is in Chinese, so.
But I think everyone can understand the problem based on the sample input and the sample output. Yes, because now the size of the sliding window is 3. So at first the sliding window is from 2 to 4, and the maximum
second slide window.
and the maximum
yeah.
is 4. So the first return value is 4.
And the second slide window is 3, 4, 2, and the largest number is 4.
Yes, and the next one, 4 to 6, the maximum number is 6. So if we continue doing this, the result is like this. And Yihan wrote another, maybe not one bug, maybe some bugs.
Yeah, several bugs maybe.
Yes, well, it seems too long. It shouldn't be that long.
I think many of the programmer are familiar with this problem solution, so we're just focusing on the debugging process.
Yes.
So here is what we got.
So this is check the bound.
Corner case.
Yes,
bound.
corner case. Okay, it seems okay. Size.
So first, for every element in the vector num, starting from the first element. So if the DQ possible max is empty, then we add the element to the back of the DQ.
Yes, the double-ended queue. Okay, yes. So, and if the current number is larger than the last value in the deck,
yes,
we pop. Okay, so that's a problem. First, you push a value into the deck, and then you check if this number is larger than or equal to the last number. So will it always pop itself? Pop. Because first you push back the number I, and then you just pop it back.
But I thought, remember, look the next code, because I pop back the last element of the queue, but then I add it back. So does it work?
So you pop back many values and then push back.
If there is only one element.
Okay, so if there are two elements, you pop one element and then you push back the current number, and you pop another element and you push back the. I don't think it works because you push back this current number, it becomes the last element in this stack, and you will pop it out again. You push this back, and it becomes the last value in the double-ended queue, and you just pop it again.
Oh, but why? I mean, like
okay, so now the deck is empty, and you push back let's say 2 into this double-ended queue, and now the number I is also 2. It's equal to the last element in the double-ended queue. Yes.
Yeah, of course. So if you enter this statement,
pop it back.
Yeah, pop back. Yeah.
And you just push it back.
Yeah, push it back.
So actually you did nothing.
Yeah, but it's just for the case that there's
empty.
only one. Yeah, there's only one element.
Okay, but if it is not empty, you check if the current number is larger than or equal to the last element in the deck. If yes,
for example, you can look at example there. If we go through and we met number 3, so 3 is larger than the
2. So you just push back, pop the 2 and push the 3
into the queue.
Okay, so it doesn't work well, but it works.
Yeah, okay, just fine.
But what will happen if there are several elements which are smaller than the current number? but these elements are all in the double-ended queue. You should pop all these elements and then push.
I think you can continue like
Reading
the code.
So if the current number is
smaller,
smaller,
smaller than the last element,
you just check if the
start from the front of the queue to check the first element. If the first element, the front element is smaller than the current element num_i, then I think I don't want this element. I don't want this number. I delete it. And I go through it.
Okay, so sometimes you put the current element in the back of the deck, and sometimes you put it in the front of the DQ.
Yeah, but it depends on the condition, I think.
Can you maintain the order of the order within the double-ended queue? Is it a rising order? Can you maintain this?
I think so. Because for those who are larger than the last element, I pop them back, I push them back into a DQ. And for those who are smaller than the last element,
while the current number, while the first element in the double-ended queue is smaller than the current number, you just pop the first one. Let me think about it. If it is not smaller than okay, so
what might be the problem?
give me a second. Okay, so this part seems good, but I don't really understand this part.
Yeah, but
okay, so for this one, you just check if the largest value or the last element in the double-ended queue is out of this sliding window. If it is yes, you just
if it's within the slide window, then I
push it
back the element into the answer vector.
Okay, so what if?
Yeah, I think there is a problem when like the first few elements, and like if the size is 3, then the first one, the second one element, it will definitely push. They will be pushed back to the ans vector. I think.
Yeah, so that's wrong. So if you just go to this else branch, you can you don't push anyone, you don't push anything into the answer vector for this sliding window. For this position of the sliding window, if you go to the else branch, you didn't push anything into the vector. So for this position of the sliding window, you didn't give an answer. Because I think if I found the max element in the sliding window, in one sliding window, then let me think.
So what do you think? What do you think?
Actually, you wrote a maybe strange code like this. If the current number is larger than the maximum number in this double-ended queue, you just push back the maximum number. But maybe there are also some elements which are smaller than the possible max dot back. It is possible, yes.
Yeah.
You didn't push them out.
Oh.
You didn't pop them. You just pop out the largest element, and you put this current number into the double-ended queue.
Oh, I understand. So like
So
if we have 1, 5, 7. Oh.
yes, you just pop the 7 and add maybe 9 into that double-ended queue.
So
But actually,
what's the problem?
Actually, the 1 and 5 are also useless.
Oh, so you mean I should maybe combine the while loop with?
Yeah. So did you remember what we simulated in the paper on the paper?
Yeah, I
How
think
do
we
we
first.
check? How do we check if we should pop out any element? We have a current number, and how do we check out? How do we check if we should pop out any element in the double-ended queue?
We first check if the current number is larger than the last element.
Last element, the smallest element or largest element.
So the order matters? Do you mean like with first?
Yes, I think it may not matter, but some kind of doing some kind. Maybe you check from the smallest element is easier.
So we're starting checking.
Yes, because if you check from the smallest element, you can stop until you find a larger element. But if you start from the largest element, you will need to first find an element that is smaller than or equal to the current element, and then push all the elements that are smaller than the current element out. Pop all them out. It's difficult. It's more difficult.
So I can delete these lines, just leave the while loop, because I start from the first element.
Yes.
And I loop over the DQ.
Yes.
So just like.
Yes. And you need to check if if it's empty, you just did it here. Okay. Okay. So do you really need to check if it is empty here? You can just combine it together, I think. So whatever you.
If it is empty.
Yes, I think you can combine them together. And if all elements in this double-ended queue is smaller than or equal to the current element, we need to pop all them out. Yes.
So can we make a comparison? Because if pop max is an empty queue, then there's no element in this queue. What happens if we make this comparison?
I think you will have a segmentation fault because it doesn't have a front element.
Yeah, so
you'd better to check if
we still need to remain this situation.
Yes, but I think you can combine them together.
Like what?
So if you just leave it like this, is it possible that we can pop all the elements in the possible max and we go to this and we check this condition again? Maybe there is only one element in the possible max double-ended queue and it satisfies this condition. So we pop it out, yes. And we will go to this condition again. And we will have a segmentation fault because we don't have an element. So should we check if the possible max is empty in this while loop condition?
Oh, I got it. So I should add a condition while it's not empty. Like this?
Yes. So you don't need this again.
Seems more elegant.
Yes. And whatever you do, you need to push the element into this double-ended queue. Yes. So you can just try to pop all the elements that is smaller than or equal to the current element. You pop all them out and you add it into the double-ended queue. Now you can maintain the order of the double-ended queue is from the smaller to the largest. And then you check if the largest element is out of the sliding window. You push it. Okay, so whatever you do, you still need to push element into the answer vector. Yes. So there are two possible conditions. One is the largest element is still within our sliding window.
Yes.
Another is
out of bound.
out of bound. And what should we do if it is out of bound? We can just pop it.
Right. Yeah, we should pop it.
And after we pop it, we can add the current largest element into our answer vector. Yes.
Yes, but I think if we pop it, then it's very natural to regard the previous second largest element as the largest element now.
Yes.
So how to deal with the situation when the index is less than the size here?
Index is less than the size. Okay, so you mean we don't have a complete sliding window?
Yes, we.
You can just check if the I is larger than or equal to the size or something like that.
This situation there, like.
Wait a minute. So let's first think about it. First, you need every time you do this for loop, there will be one element that is out of the sliding window, but we are not sure if this element is in our double-ended queue. Yes.
Yes.
So we can check if the largest element in our double-ended queue is out of the sliding window. And if it is out of our sliding window, we can just pop it. Is it clear?
Oh, I think that's what I did there. So what's the difference?
It's not the same. Here you check if the largest element is still within our sliding window. And if yes, you just push it back into our vector.
Yeah.
Otherwise, you pop it back and you will not push anything into the vector. And we don't get an answer. Because it is possible that here you push something out. You pop something out from the double-ended queue and it just goes to another for loop. You didn't push anything into the answer vector, but you need an answer.
Yes, I need an answer, but I mean, can you say that again?
Yes, so it is possible that in the middle of our execution, this condition can be satisfied. Yes, if the yes, if the largest number is index is out of our sliding window, this condition will be satisfied, and you just this condition will be not satisfied, and you go to the else loop, and you just pop the largest element, and you finish this time of the execution of the for loop. So you didn't execute this line. So the answer element didn't get a result from this sliding window.
I think it's a little weird because if I, in this code, if this situation is not met, then I don't know how to say that. So do you think I should?
Okay, so every time you execute the for loop, you will push an element into the double-ended queue. Yes. And
so do you think every time I should also push back the largest element into nth vector?
Don't you think so? If the I is larger than or equal to size -1.
Oh, I think I might understand. So we should execute this line every for loop and to check the situation that if we should pop the
You should first pop or first push back.
first.
Can you guarantee the here? Can you guarantee the maximum number is still within our study window?
If it's not, then if this element is out of bound, then I should not add this. I should not add this element. Instead, I might. I don't know, but if I pop out this element and I found that it is out of bound, so I push back the second largest. So do you mean? Oh, yeah. Back.
Pop doesn't need to take an.
Erase.
What do you want to do? Pop doesn't need to take an argument. It just pop the last element.
But ans is a vector. It's not a.
Oh, answer is a vector. So why do you want to pop back something from the answer vector?
So should we use something like erase?
What do you want to do?
So now, I mean, in this step, we should check what to add to our ans vector, right? So we need to know to like add our to check if the largest element is within the sliding window.
Yes.
So if it is not, then we do not add it into the vector, and we add the second largest.
Yes.
So the first thing we should do is to check the condition.
Yes, to check if the largest element in answer or in deck. In this vector or in this possible max.
To check the answer in.
To check the largest element in answer or possible max.
I'm sorry, could you repeat your question?
Yes, so now you need to check if the largest element in possible max or in answer is still within the bound of the sliding window.
The value in possible max.
Yeah, so what should we write the answer here?
Oh, I know, maybe.
Okay, so now you can check if the
if possible max the last element is dot pop, no, and back dot first.
What is the first, the value or the index?
Oh, I'm sorry, the second.
How to check if it is still within the bound? So now the right bound is I, yes.
The right bound is I, yeah.
Yes, and the size is size. You need to check if this possible max dot back dot second is still larger than or equal to the left bound.
I think we should. So first, I think should not be the first few elements. So I think it should larger or equal than size.
Now you are trying to check if the largest element in the double-ended queue is still within our bound. We are not push anything into the answer. If you are pushing something into the answer, you need to check if you have had a complete window. If
Oh, I got it.
Yes.
So
if it is, you need to check if it is smaller than the left bound. Yes.
Smaller than the left bound? Larger than the
What you want to do that? You want to pop the largest element if it is out of the bound. Yes.
Yeah.
So should you check if it is in the left of the left bound?
Oh, so do you mean equals to I don't think will be larger than I, so
Yes, it can be larger than. Is it I minus size or I minus size minus 1 or I minus size plus 1?
+1.
Yeah. Or you can also change the smaller to smaller than or equal to. Either is okay.
If so, then we think it is not within the bound and it's not within the bound. So I want to publish a lost element.
Yes. That's not good. Let's change this.
And lost element.
Do you think it can compile?
Oh no. First.
And the final thing, you need to check if this sliding window has complete has. So if I is 0, can't push anything to the answer. You need to check if I has been larger than or equal to size minus 1 is. You need to check if we have a starting window now. If we have a completed starting window, if we have a. Seems good.
Make a test. It's so exhausting.
No, it's not correct.
Oh, sorry.
It's not correct. I didn't give the first size or size minus 1.
Size means
Size or size minus 1. Yes, let me check. Yeah, something is wrong. It's correct.
oh, I hate this process.
So it didn't. So if there are some minus numbers, there are some negative numbers, your program will be wrong. Let's check why this happened.
Why? Why should we have oh no.
Something unsigned. The size is unsigned.
Yeah, the size is unsigned.
I minus 1 plus 1. Oh yes, maybe the I minus size will be negative, but something will happen because if
Oh, so it should still. I mean, it should meet these conditions. So
wait a minute. Size minus 1 because size can't be 0. So anyway, it is okay. The size can't be 0. So size minus 1 must be larger than or equal to 0. So here there will be no problem. But here the size, the I minus size may be less than 0. The size is
it's
unsigned.
unsigned.
So it will be a very large number.
number.
I'll just maybe cast the size to it.
You mean?
Cast the size to it is okay. Size.
Wow, where should I make the casting?
Just for the size. Now if I minus size plus 1 is less than 0, it will be just a negative number instead of a very large number. That's it. Why this happen?
But why? I mean, size is unsigned, and
because
I minus size,
it will become an unsigned long.
Oh, so if it's negative, then it will be a very large number.
Yes. I'll try that. I'm not sure if it will fix this bug, but try that. Okay.
Oh, it's so exhausting.
Yes, I guess. Do you want
like
to
write the code for 10 minutes and debug it for 1 hour.
Yeah. 你写了好多 bug 呀，你写了好多 bug 呀，但其实你觉得这个有用吗？ If the size of the number is 0, this will be just
you will not enter this loop.
Yes, if the size is 0, I don't think okay, so anyways, this one can be deleted. And size is larger than number of size.
Also move it.
If size is larger than number of size, will it be wrong? Size is larger than number of size. Okay, so it will not push anything to the answer. It should be correct. Yeah. Because the size is larger than number of size, and this condition will never be met. So the answer will be also empty, and you don't need to check this. The size is equal, I think you should check that. And this is also correct.
Maybe so. Yeah, we finished.
想说一个结尾吗？
No.